So in the previous power lecture, we discussed the MMA algorithm and we discussed how can we use it to minimize some initially difficult loss function. And in this power lecture, we will discuss how we can use MMA to minimize the loss function in the L1 norm regularized least square regression. So the loss function that we have in the L1 norm regularized least square regression is G of W, which has two terms. One is y minus phi times w, additive norm of this term, plus lambda times the L1 norm of the weight vector. So let's call this function as E of w, and let's call this as R of w. So our loss function becomes E of w plus lambda times R of w. And now to minimize this loss function, we can sort of like minimize, first we can learn how to minimize this first term, and then we will combine, we will try to minimize a combined loss function which will drive the ISTA algorithm for us. So first we'll consider the minimization of the first term in the loss function, which is E of w. And this results in an iterative algorithm using MMA, which we call as Landweber iteration. So now we'll see what it actually is. So the loss function E of w, I'll just erase it to avoid clutter. So the loss function E of w is norm of y minus phi times w, where, as we discussed in supervised machine learning, y is a vector of target values, phi is a feature matrix, and w is an n-dimensional real vector. Right. So we had seen the minimization of this function in the linear regression lecture. We have seen it in the L2 regularized least square regression as well. We have seen the normal equation based solution. Which requires us inverting a matrix phi transpose phi. It requires computing the inverse of this matrix, and this matrix is an n by n matrix. So if n is very large, this can be very difficult to invert actually. And even if the n is not large, let's suppose the resulting matrix phi transpose phi is ill conditioned, then inverting the matrix can turn out to be very difficult, even though n is not very large. And furthermore, we also saw the grain descent algorithm. But grain descent tends to be sometimes very slow to actually solve this problem. So today we'll discuss a better algorithm known as the Landweber iteration, which comes through the mesh and minimization algorithm that we can use to minimize this loss function without requiring us to invert this matrix. So for the sake of completeness, we'll discuss the minimization of this loss function using the normal equation. Just for completeness, we have shown it earlier in the linear regression lecture as well. We'll just like expand this loss function. E of w is equal to y transpose y minus twice of y transpose times phi times w plus w transpose phi w. And since this is a convex function of w, we can set the gradient with respect to w to 0 to compute the optimal solution. So by setting the gradient equal to 0, we get twice of phi transpose y plus equal to twice of phi transpose phi times w. So we can cancel 2. And by inverting this matrix, we get the solution as w star is equal to phi transpose phi inverse phi transpose times y. So as we can see, it requires inverting this matrix, and this matrix may be ill conditioned. For example, what is the condition of a matrix? So let us denote the let's suppose the eigenvalue of this matrix is denoted as, it would have n different eigenvalues, sigma 1 to sigma n. So the condition number of any matrix is defined as the ratio between the minimum eigenvalue of phi transpose phi over maximum eigenvalue. So if the condition number is 1, it means that the matrix is very good condition, and if this number is very small, then it means that the if we try to like inverting this matrix can be very difficult. There's a better way of understanding as to what role the condition number plays in the minimization algorithm. If we talk about the second order methods like the Newton, the Newton's method or the Newton-Raphson method. So any algorithm that uses the second order information of a function, the convergence rate of that algorithm is heavily dependent on the condition number of the matrix. Or like if we try to use the second order method, we'll find that this matrix is a Hessian matrix, and the condition number of a Hessian plays a significant role in the convergence rate. So these are so we are not going to discuss all of that into this lecture, but just for the sake of completeness, there's a condition number, and this can be very low in typical minimization problems, and that's why even though the n is not very large, inverting this matrix can be really difficult. So we will now discuss a better algorithm that computes the solution for minimizing this loss function iteratively, that is much better in terms of rate of convergence as compared to the gradient descent algorithm, and as well doesn't require inverting any matrix like the matrix phi transpose times phi. So now we will discuss what this algorithm is, and what this iteration is. This is known as Landweber iteration, and we'll arrive at that solution using the majorization minimization algorithm. So let's see how we can do that. So now we will construct a function g of k or simply a function g that will allow us to minimize this loss function a of w without requiring to invert this matrix. So as we discussed earlier, the function g of w should be such that it satisfies the two constraints that we discussed earlier. Along with that, it should be a function that is easier to minimize, perhaps a convex differentiable function, because the original loss function a of w is both convex and differentiable. So it would make sense only if g of k is also a convex and differentiable function. So the g of k should satisfy the one property, is that it should be greater than or equal to j of w for all w in the domain of j. So we can perhaps construct this function g k w. We can drop the subscript k for now, because currently we are just discussing a general function rather than discussing the particular iteration. So I'll just drop this subscript k for now and just write it as g of w, just to avoid some clutter or confusion. So we can select g of w as some function which is, sorry, here instead of g of w I should have written e of w, because currently we are minimizing the function e. So this function should be e of w plus some function of w, let's call it f of w, where this function is non-negative and perhaps convex as well as differentiable. So that would ensure the convexity and the differentiability will ensure that we can perhaps minimize the resultant function by just setting the gradient equal to 0. So that would be an added advantage in this majorization minimization step if we can do that. So for the L2 loss function, that is our E of W, is simply equal to L2 norm of y minus phi times W. So to derive the ST algorithm, or to minimize this loss function, we can construct f of W, a function that will eventually cancel out this term phi transpose phi in the entire function. So let's see how we can do that. So we'll just state the function f of W that will select to minimize this loss function E of W by minimizing this function G of W. So here is a choice of our f of W. So G of W becomes E of W, which is norm of y minus phi times W squared plus W minus, now we can incorporate the iteration number k, because here we will have dependency on the kth iteration, minus Wk, that is a solution for the parameters W at the kth iteration of this algorithm. So Wk times some parameter beta, where beta is a scalar and beta is greater than 0. So beta belongs to the domain R plus, that is non-negative real axis, times an identity matrix I, which is an n cross n identity matrix. This is of the same dimension as W, n cross n, where W is n-dimensional real vector, minus phi transpose times phi times W minus Wk. So as we can see, this function f of W is quadratic in W. So this is just some matrix M, and this is just some vector. This is a known vector, this is a constant. So this is a quadratic function in W, and it would be convex and non-negative if this matrix M, which is equal to beta times I minus phi transpose times phi. So if this matrix M is positive semi-definite matrix, then this function f of W would be both non-negative, a convex and differentiable function of W. It would be non-negative because for any matrix S which is positive semi-definite matrix, for any positive semi-definite matrix we have that V transpose SV is greater than or equal to 0 for all V in Rn. So this is a property of semi-definite matrices. So you take any n-dimensional real vector where n is the same as the dimension of this matrix n. So we take any vector n, we take any vector V in the real space, and we do this V transpose SV. It will be greater than or equal to 0 if S is a positive semi-definite matrix. So if S is positive semi-definite matrix, this function would be non-negative and also would be a convex function, because you can compute the Hessian of this function, and the Hessian would be simply matrix M times some scaling factor, which is we denote by just C. So some scaling factor times the matrix M, or perhaps it won't be there, but perhaps some scaling term like twice of M. So that would be the Hessian of this function, and if this Hessian is positive semi-definite matrix, then the function f will be a convex function. So now the question is, but it would be positive semi-definite matrix if we select beta such that beta times I minus phi transpose phi is a positive semi-definite matrix. And this matrix would be positive semi-definite if we select beta equal to the max eigen of phi transpose phi, where max eigen of phi transpose phi denotes where max eigen of phi transpose phi denotes the maximum or the largest eigenvalue of this matrix phi transpose phi. So if we select beta, which is greater than the largest eigenvalue of this matrix phi transpose phi, then the entire matrix beta times I minus phi transpose phi would be a positive semi-definite matrix. And we assume that we'll select beta such that it is greater than the maximum eigen or the largest eigenvalue of the matrix phi transpose phi. So this is the choice of f that we'll select to minimize this loss function. So we have gk equal to gk of w equal to the L2 norm or the function e, which is y minus phi times w norm squared, plus function fx, which is w minus wk transpose times beta I minus phi transpose phi times w minus wk. So this is the function gk, and since this term is always greater than or equal to 0, gk satisfies that gk of w is always greater than or equal to e of w, where this is the function e. Furthermore, if we put w equal to wk, then this term becomes 0. So gk also satisfies that gk of wk is equal to e of wk. So now we will minimize this loss function gk. Furthermore, this function is convex and this function is also convex. So we can obtain the minimizer of the loss function gk by just setting the gradient of this function to 0. So now we'll see the solution for or the minimizer of this function gk.